Good evening, everybody. I hope that you have had a wonderful weekend. We are going to start chapter 5, and chapter 5 is all about gases. I think that as I'm going through this, you are probably going to recognize a lot of the things from General Chem. And so this first part of the chapter will go through fairly quickly, and then the second half of the chapter will slow down quite a bit. And again, we should know that gases are obviously very, very important for our life and acts as a sink for many of our waste gases that we put into the air from our industry. And so we're going to study a little bit on that. But the hardest thing about gases is studying them. It's a little bit easier to study solids and liquids. So the first thing is the Torricellium barometer, which was used in 1643. And you can see that it has mercury, and it talks about mercury as 760 millimeters of mercury for standard atmospheric pressure. And we'll be talking about STP. Hopefully that rings a little bit of a bell here. And why are we using mercury? Well, mercury is something that has a very high density. If you recognize, the density of water is 1.0 grams per milliliter, and the density of mercury is 17.8. But it is a liquid at room temperature, and it feels difference in temperature very, very easily as compared to anything else. And so they found this out very early. Now, in measuring atmospheric pressure, we have this closed system on this end and an open system here that you can feel the atmospheric pressure. Well, in this first situation, the atmospheric pressure is very great because it's pushing the mercury up through the tube here. And if remember, you have these gas particles that are in here and they are colliding and they're creating some pressure, but it's far less than the atmospheric pressure. Conversely, on the other side, if we look at this other one, we can see that these particles here, when they are colliding, they're creating a lot more pressure, and so the mercury is going in the opposite direction. We will see this in class because we do have some manometers, and we'll take a look at vapor pressure through them. So pressure is equal to force over per unit area. Those of you that are in physics right now, you've probably been studying the Newton over meters squared, which here we're going to call this a Pascal. And this is just one of the units that you will see for pressure. You can see that 1 atmosphere is 760 millimeters of mercury. These are the two that we will often use. Textbook and AP does like to put in the unit torr, which is the same as millimeters of mercury, and you can see it's equal to 101,325 pascals, or 14.7 pounds per square inch. Okay, so as continuing on for measuring pressure, here is one that is used by Boyle, and you might recognize Boyle's law. And a couple of you that are in math class right now came and asked me and said that you were using Boyle's law in math. So it's great how those two subjects come together. So you can see that the difference in the height here of our mercury depending upon the pressure that it's feeling. And he was able to come up with Boyle's law. And if we take a look at Boyle's law data from this, you can see that as the volume is increasing, the pressure is decreasing. And this over here would be an inverse relationship. If you pay attention to our x and y axis, you can see that I have volume and then 1 over the pressure. And so this is all going to be true for low pressures. This is going to be very true. And if we go to high pressures, Boyle's law doesn't work quite as well, and we need a little bit of correction factor. However, the deviations are very small. So if we take a look at a couple of pistons here, you guys can see that the volume of sulfur dioxide gas, if I have the volume that here you can see 1.53, I have a certain amount of pascals, so that you should recognize that as pressure. And if I increase that pressure, what's going to happen to the volume? The volume is decreasing. And so that is simply Boyle's law. Pressure and volume are inversely related, and another way that you will see it a lot is pressure times volume is equal to a constant. And you can see pressure times volume equals pressure times volume in the beginning and ending situation. One thing that you need to make sure that is also held constant is the number of gas particles. So the number of gas particles is going to be held constant. Okay, I'm sorry, that is my son just walked in here and interrupted me. So that is going to be held constant. So if we take a look, a simple Boyle's Law problem, I have a sample of neon gas has a volume of 9.80 milliliters, three significant figures there. I have a pressure of 437 pascals. I do not need to convert this to anything. It doesn't matter what unit of pressure you have as long as they're the same. The same goes for volume. You can see I have milliliters here and milliliters here. So you guys should be able to go ahead and put that into the formula, and you should recognize that pressure is 714 pascals. So this is very simple little math. I will let you guys do that yourself. And if you want, you could also take a look at changing the pressure into atmospheres. And if you do that, you should get 0.00705 atmospheres for this situation. So we're at very, very low pressure. Make sure that you can do that. Okay, so now we're going to go on to Charles' law, which is another one that should be reviewed. So we had Boyle's law, which had to do with pressure and volume, and they were inversely related. As pressure increased, the volume is going to decrease and vice versa. So with Charles' law, we are talking about volume and temperature. Now you can see that this came along a little bit later, and you can see that these gases are decreasing, decreasing, and decreasing. And they are all coming to this point right here, negative 273.2 degrees Celsius. And this is a point that we are talking about absolute zero. Well, you might be asking yourself, why are all of these slopes different? If I go y equals mx plus b, I'm going to find that the slope is different. Well, you can see that I can have different moles of the gas. They are all going to have different amount of moles because their molar masses are going to be different. However, that doesn't matter. I continue to cool them down, cool them down, cool them down, and I am reaching the same exact extrapolated point. Now, in Charles' law, we have gotten very close to absolute zero with our modern day technology that we have. You can see that I have a Kelvin here, and right now we are looking at that we have actually gotten to 1, 2, 3, 4, 5 kelvins within absolute zero. And so keep in mind that the molecules are vibrating very, very slowly, and we virtually would have zero matter at this point. Okay, so if we go on with Charles' law, we can see here that volume and temperature is a direct relationship. So as volume increases, temperature is also going to increase, and that becomes a constant. And so in general chem, you probably saw the formula in this manner. V1 over T1 equals V2 over T2. Again, the only thing that we have to make sure about this is that our temperature must be in kelvins. So we have to have that Kelvin scale. And the Kelvin scale, again, you remember you take degrees Celsius and you're going to add 273 to that value, and you are going to get kelvins. Excuse me, kelvins there. So the only way that Charles' law is true by putting the temperature always back into kelvins. So again, you can see here they have just cross multiplied for you. Volume 1 times temperature 2, volume 1 times temperature 2, volume 2 times temperature 1. So either formula will work. This should be given to you probably on your AP Gold sheet. It is something that's pretty easy to remember though. So the only thing you need to remember here is we have volume, we have our temperature in degrees Celsius, you need to move that to Kelvin, and again, we have degrees Celsius here. You have to put both of these into Kelvin, and when you do that, go ahead and calculate this out. You should get your new volume equal to 3.11 liters. Again, paying attention to significant figures. We have three significant figures and all our given information that is here. Okay, a couple more slides here. We've been going for 9 minutes. We'll finish this first section. So we're talking about Avogadro's law, which leads into the kinetic theory of gases. And if you remember Avogadro's law is that each balloon holds 1 liter of gas at 25 degrees Celsius and 1 atmosphere. Another thing that you can add on here is that they are going to have the exact equal number of particles. Oh, sorry. Whoa. Just like writing on my smartboard. So it's equal number of particles in this situation. And so this leads up to the ideal gas law. Avogadro's law says that equal volumes, excuse me, that would be my son. Um, Avogadro's law is that equal volumes at the same temperature and pressure contain equal number of particles. So we learned in General Chem that 1 mole of any gas, oh sorry, my pen is 1 mole of any gas, let me try that again, is equal to 22.4 liters. And remember that this has to be at STP. So we have P at STP. So if we take a look, we have to have standard temperature 273 Kelvin. We have to have 1 atmosphere or 760 millimeters of mercury. And so what he figured out then is that in this situation, the volume is directly related to the number of moles of the gas particle is equal to a constant. So we have volume of gas, N is the number of moles of gas particles, and A is just a proportionality constant. Again, it's just another way to look at it if you don't have a balanced equation, that you can take a look at the volume compared to the number of moles that it has and see um, the number of particles of how that gas is going to act. And we're going to be using this now when we go into the ideal gas law. Okay, that's it for our first little podcast. I hope you're doing well, and I hope that a lot of this was review.